In this video, we're going to look at factors that determine the strength of our acid. So factors that determine acid strength. So eventually what I want us to be able to do is, given an acid-base reaction that's at equilibrium, like we were given in the last video, but not given pKa values, be able to determine whether reactants or products are favored at equilibrium. So we want to be able to look at the structure of the acids, use the factors that we're going to learn in this section, and be able to reason through it just based on the structure itself without being given those pKa or Ka values. For a lot of these, what we want to keep in mind when we're determining the relative acidity, we're going to look at that conjugate base. Remember, the acid is forming the conjugate base. If the products are more stable, we're more likely to form them, right? Things don't want to form things that are less stable. We want to form things that are more stable. So a lot of times the factor that's going to affect it is the stability of the conjugate base. So when determining the relative acidity, we're going to consider the conjugate base. So look at the conjugate bases. Right? The more stable the conjugate base is, the more likely it is to form, the more likely that acid is to donate its proton. So the more stable the conjugate base, the more acidic the acid. Right? We want to form things that are stable, not things that are less stable. So the more stable the product is, the more reactive the reactant is, right? The base is my product, the acid is my reactant. So I just want to keep that in mind as we go through these. And the first one I want to look at is resonance. So resonance effects. And I am doing these in a slightly different order than your text. The text does resonance kind of towards the end, but I think it makes the point about the conjugate bases being more stable easier to understand if we do this one first, because it's the most pronounced of the ones that we're going to go through. So our first one, resonance effects. So if a structure has resonance, we already know that it's more stable than one that doesn't. Remember, when something has resonance, what we're doing is we're delocalizing those electrons. And if we can do that, it's less reactive. Again, chemical reactions involve electrons. So if I'm kind of spreading them out over the entire molecule, they're not as able to react. So anytime we have resonance, it's going to be more stable compared to something that doesn't. So if the conjugate base is resonance stabilized, meaning it's stabilized by resonance, then its corresponding acid is more acidic. So if I was to compare this acid, so this is acetic acid, its functional group is a carboxylic acid, and we'll talk about those in chapter 3, functional groups, that is, not necessarily carboxylic acids. And this is an alcohol. So comparing my carboxylic acid to my alcohol, my pKa for the carboxylic acid for acetic acid is about 4.8. And my pKa for this alcohol, this is ethanol, is 16. So we know that this one is my stronger acid. And we know that right now just based on the fact that I gave you the pKa values. But if we didn't have the pKa values, right, what's going to happen, right? This is going to react with some sort of base. The base is going to take the proton, and I'm going to end up with this as my structure. So negative charge, 2 lone pairs. Right, there was 2 lone pairs up here initially. It just took the proton, leaving 3 lone pairs on that oxygen. If I do the same thing with my alcohol, we're going to react it with a base. It's going to lose a proton. Again, keeping the lone pair, it had 2 on that oxygen. Now it has 3. That's what we get. And if we look at these 2 conjugate bases, my acetate ion, the one on the left, has resonance, right? So this one is resonance stabilized. If I look at this one, we have no resonance, right? I have an electron source. There's lone pairs on that oxygen, but there's no receptor. There's no place to put them. That carbon in the middle here, this has 2 hydrogen on it. So if I was to try to move electrons to it, I would end up with 10 electrons on that carbon, and I can't do that. So no electron receptor on that one. No place to put electrons. So because my acetate ion, right, my conjugate base of acetic acid is more stable, I'm more likely to make that, right? Essentially, that's what we're looking at. We're saying of these 2 products, because these are my products, which one is better? This one with resonance is better. It's supposed to be a bracket because it is stabilized by resonance, right? Our electrons are delocalized. Means it's more stable, which means we're more likely to make it. Right, compared to my deprotonated alcohol. So the original acid is more acidic than the alcohol. So be really careful wording that trips people up every semester, because at some point I'm going to give you kind of a typical question. We'll go back up, is I'll give you those 2 acids, the ones we started out with here, and I'll say which one is stronger and why. I will not give you these values. You're going to look at the conjugate base, because we remember that if the conjugate base, right, is more stable, then its corresponding acid is more acidic. So we're going to go down and look at the 2 conjugate bases. We're going to see that this one has resonance, this one doesn't. Because this one has resonance, my acid is stronger. This is where people goof up, is they'll write a sentence very similar to this one I just wrote. They'll say it has resonance, or the electrons are delocalized, so it's more stable, making it more acidic. Don't use the word it. It is not more acidic, right? It, in this case, if you use this sentence, it is my conjugate base, right? This is my base, not my acid. So if you're saying it is more stable because it has resonance, so it is more acidic, no, right? This thing is not more acidic. This thing is more stable. It is less reactive. What's acidic is the acid, not the conjugate base. So be really careful. I would just avoid using the word it, because I will take off for that, because no, it is not more acidic. The original acid is. And if you say the acid is more stable because it's resonance stabilized, so it is more acidic, then you're going to lose points because it's not the acid that's more stable. The acid's more reactive. The base is more stable. So you're explaining, right? Let me just be really clear so you guys don't lose points on this. This that I'm circling right now is more stable. So this that I'm circling right now is more acidic. So please make sure you differentiate between the two. You need to be really clear that the product is more stable, so the reactant is more reactive. Hopefully that's making some sense, so you guys don't lose points just based on how you're writing your sentence. So anytime we have resonance, the thing that has the resonance, my product here, is going to be more stable, making the reactant, my acid in this case, more acidic. The second factor we're going to look at is element effects. So element effects is really just looking at some trends on the periodic table. I do want you to be able to explain those trends though. So we're going to have one for going across a period and then another one for going down a group. So across a period on the periodic table, the acidity of HA, so A just being a generic conjugate base again, increases as the electronegativity of A increases. So be careful on these. Our trend is going to be different for going across than it is down. So going across, the acidity is going to increase as the electronegativity increases. So our example, if I was to look at carbon bonded to a hydrogen, and then that carbon is going to be bonded to 3 other things, so it doesn't have a charge, right? It has its octet. And some common nomenclature in organic, if you see an R, it literally means the rest of the molecule, and we don't really care what it is. So it could be 3 other carbon groups, it could be 3 hydrogens, it could be 2 carbon groups and a hydrogen, it doesn't really matter. It literally means the rest of the molecule. So it's just our way of saying that carbon is bonded to 3 other things, and we don't care what it is. So usually it's going to be a carbon group or a hydrogen. Again, I only care that there's 3 other things bonded to the carbon, so I don't have to give it a charge. So I'm drawing one of the hydrogens out. It could be more, but again, remember we're doing Bronsted-Lowry here, so I'm talking about losing a hydrogen, so I need at least 1 hydrogen attached to it. I'm going to do the same thing with nitrogen. It's bonded to a hydrogen, and then it's bonded to 2 other things, so it's also not charged. Oxygen bonded to hydrogen, and then it's bonded to 1 other thing. It could be a hydrogen, and then it's water. It could be a carbon, and then we have an alcohol. And then fluorine bonded to that hydrogen. So as we go in this direction, my atom, right, carbon, nitrogen, oxygen, and fluorine become more electronegative. What that means for us is that bond is more polar. We can think about it that way, so it's easier to break. We can also think that, remember we're looking at our conjugate base. So our conjugate bases in this case, I have a lone pair and a negative charge on carbon. I have a lone pair and a negative charge on nitrogen. It actually would have 2 lone pairs because there was 1 to begin with. I would have 3 lone pairs, there was 2 to begin with, and a negative charge on oxygen. Fluorine would actually have 4 lone pairs, there was 3 to begin with. But the point is, remember, we like negative charges on more electronegative atoms. So the stability of my conjugate base does increase in this direction. Again, if our conjugate base is more stable, we're more likely to make it meaning my acid is more likely to lose its proton. So more stable conjugate base as we go across, right? The negative charge is on the more electronegative atom. Which means as I go, I'm going back up to my acids here, it's more acidic in this direction. So HF is more acidic than the hydrogen bonded to the oxygen versus the hydrogen bonded to the nitrogen, and so on. The reason for that is that the conjugate base is more stable. Why is the conjugate base more stable? Because the negative charge is on the more electronegative atom as we go across. So fluorine can tolerate that negative charge better than oxygen can. Carbon doesn't really like that negative charge at all, making it not very stable, making the hydrogen bonded to that carbon not acidic and likely to donate. In fact, it's just not acidic. We're not going to see that. We're not going to generally just pop hydrogens off of tetrahedral carbons. It doesn't happen. So as I go across, more acidic. And as with the resonance effects one, at some point I'm going to give you a couple acids that would fall under this effect, and I would ask you to pick the stronger acid and tell me why. And if you just write because of element effects, I'm not going to give you credit for that. Like, what about element effects? And if you just say they get stronger as you go across the periodic table, I'm going to ask you why, and you're still not going to get credit for it, right? So please be specific. They do get stronger as you go across a period in the periodic table because the conjugate base is more stable. And if you just say that, I'm going to say why. And you're going to say because the negative charge is on the more electronegative atom. So please be complete, right? This one is a stronger acid, right? My alcohol, than this, which is an amine. My alcohol is stronger than my amine because the conjugate bases, right, in the conjugate bases, it's better to have the negative charge on an oxygen than a nitrogen because it's more stable. So please be specific. If you just give me the title of the effect, you're not explaining why. You're just giving me the title. So please explain when I ask you to explain for full credit. Our second trend, we're still under element effects. So we have two of these, right? I said one going across a period and one going down a group. So down the group, of the periodic table, acidity increases as the size of A increases. So remember, as we go down, we're adding electrons to larger and larger shells. So the size of that atom is bigger, right? If I look at fluorine, my outermost shell is shell 2. If I look at bromine, my outermost shell is shell 4. So as we go down, larger and larger shells are occupied by electrons, making the size of that atom larger. So down a group, acidity increases as the size increases. Now be careful to not get these two trends mixed up. As I go down a group, it actually becomes less electronegative. As I go up, it becomes more electronegative. So be careful. Electronegativity applies when you're going across. It's not going to apply as we're going down. As we're going down, we're going to look at the size. So my example for this one, and we can just stick in group 7A, so looking at our halogens, HF. I'm just going down, so fluorine, chlorine, bromine is next, and iodine. So as I go this way, it's more acidic. And you can explain this one two different ways. One, looking at the conjugate base. That's how we're going to do all of them, except there is an alternative explanation for this one that I will accept, and that has to do with valence bond theory. So let's do the conjugate base first, and I'm just going to compare fluorine to bromine. So again, do not use electronegativity. If you say that fluorine's more electronegative, so it would rather have the negative charge, you're going to get this incorrect, because that would make the HF the stronger acid, and it's not. HBr is. So electronegativity is not the answer here. This actually has to do, again, with the size, right? As the size of A increases. So because bromine is bigger, we can say that it's more polarizable. That would have been a word that you were introduced to probably in 151. Basically, it means that it can handle that charge better. It's polarizable, just means it's kind of big, it has lots of electrons, it's easy to distort those electrons, it can absorb extra, it just has more stuff going on, so it can stabilize that charge better. Maybe that's the better way to say it. So it's larger, so it can better stabilize the charge. Right? It is more polarizable. I probably shouldn't have just erased it. So the charge is stabilized better when it's spread out over a larger volume. So fluorine is smaller, it's less polarizable, it's less able to stabilize that charge, right? It's not spread out over a larger volume. The other way you can look at this one is just looking at valence bond theory. Remember, valence bond theory says that when a covalent bond forms, we're overlapping orbitals, and those bonding electrons are found in the overlapping region. And it said that if it has better overlap, it's a stronger bond. And then we said better overlap comes from similarly sized and shaped orbitals. So if I was to look at HF, fluorine is in the second shell, and then hydrogen. And then look at HBr, bromine is in the fourth shell, so its orbital is bigger than that of fluorine's. Hydrogen is the same size. That's supposed to be a sphere. Sorry, that's pretty ugly. But this is more mismatched. So it's a weaker bond. So easier to break. This take on it isn't actually looking at the stability of the conjugate base, it's actually looking at that HA bond itself, right? I'm saying that this bond between, right, hydrogen and bromine is weaker because the orbitals that are overlapping to form that bond aren't matched very well, right? They're not similar in size. One's a 1s, the other's a 4p. So it's easier to break that bond. And that works fine also. So I'll take either of those explanations. Again, what I won't take is just saying because it's further down on the periodic table. I'm just going to say, why does that make it more acidic? Stating a trend is never the answer to that trend, right? It's just stating the trend. So be careful for that. Inductive effects is our third one. So be careful with inductive effects. Every semester I will have students confuse inductive effects with element effects, and I'll try to make it as clear as I can, but do pay particular attention to this, and if you have questions on the difference, if you're not getting it, please ask me at some point. So what inductive is it's the pull of electron density through a sigma bond caused by electronegativity differences. So the pull of electron density through a sigma bond that is caused by electronegativity differences. and it's generally stabilizing, right? Remember, anytime we can delocalize electrons, if we can spread it thin, then it's more stable. So here, we're not spreading it thin by resonance, but we're still spreading it thin through inductive effects. Instead of the electrons being sit in one spot, they're being pulled through that bond, which means, again, in effect, I'm spreading it thin. I'm spreading that electron density out, so I'm making it more stable. And this one's probably going to be easier to just look at an example. So I'm looking at my alcohol here. And then I'm going to compare it to another alcohol. But on this one, I'm going to stick a fluorine on this atom. So there's a fluorine and a hydrogen there. On this one, I just have 2 hydrogens. I'm going to remove those hydrogens for clarity in a minute. And then the last carbon is the same on all of them. They have 3 hydrogens, or on both of them. So let's get rid of that mess. So this is the part that's kind of confusing for folks. In both of these cases, the bond that we're breaking when I go to form my conjugate base is an OH bond, right? I broke that bond right there, the one I just put some highlighted yellow on. When I react this one with a base, I am breaking the exact same bond. I am breaking that bond between oxygen and hydrogen. So the difference between this one and element effects is with the element effects, the bond that I'm breaking is different, right? If I go back up to just even this one, for this one I'm breaking the bond between hydrogen and fluorine, right? Between hydrogen and carbon, hydrogen and bromine, hydrogen and iodine. So if I'm comparing these two, the bond that I'm breaking is different. It's a hydrogen-fluorine bond versus a hydrogen-bromine bond. If I go up to these ones, again, the bonds that I'm breaking are different. The bond between carbon and hydrogen versus the bond between nitrogen and hydrogen. If I go back down to my element effects one here, the bond that I'm breaking is the same in both of these examples. I'm breaking a bond between oxygen and hydrogen and a bond between oxygen and hydrogen. So please don't say the one with the fluorine is better because fluorine's more electronegative and it can better stabilize that negative charge. The negative charge is not on fluorine, it is on oxygen, right? I'm breaking the same bond. And if you say, well, it's more mismatched, it's the same amount of mismatch because it's the same bond, right? In both of these, I'm breaking an OH bond. There is a difference though, and that's the fluorine on the one. But again, that's not the bond that I'm breaking. So just be really careful on your wording here. It's all these little things where people will lose points. You want to make sure you're talking about what's actually happening and you're breaking the bond between hydrogen and oxygen in both of them. However, that fluorine does cause inductive effects on this one. So I have these electrons and I have the same number of electrons on both of them. But because I have this electronegative fluorine here, right, we can put our bond dipoles on. I'm actually taking those electrons on oxygen and I'm kind of spreading it out and up onto fluorine. So you can think of those electrons as being spread out over here. Those fluorine is like pulling those electrons away. So I'm stabilizing those electrons inductively. We could say it has an inductive, the fluorine has an inductive withdrawing effect. Right? It's inductively withdrawing those electrons versus resonance. So the fluorine can stabilize the conjugate base by withdrawing electrons inductively. And again, remember, the more stable the conjugate base, the more likely we are to form that conjugate base, meaning my acid is more likely to lose its proton. So the fluorine can stabilize the conjugate base inductively. So it's more stable then my other one, so this one is more acidic than this one. Again, be careful in using the word here. Don't say it's more acidic. Your conjugate base is not more acidic. The original acid is. So just be really careful on that wording. So we're essentially spreading electrons out inductively. They're not really kind of sitting just between the oxygen and carbon, or just on that oxygen, or just between carbon and fluorine. They're being spread out. So again, back to our original, if the conjugate base is more stable, then you're more likely to make it, meaning your acid is more likely to donate the proton. So this time we're inductively stabilizing that conjugate base. And that effect is stronger if it's closer to the thing that it's stabilizing. So if I was to look at this one versus, oops, I didn't mean to do that. Putting the fluorine over here. And then it's also stronger if it's a more electronegative atom. So if I was to put a chlorine here instead, as I go in this direction, it's going to be more stable. So if I was to put a proton on there, the proton, or the acid, would be more acidic. So this first one, the fluorine is closer to the oxygen than it is in this molecule, right? The first one, it's on the first carbon, right? It's adjacent to the thing that is stabilizing. On the second one, it's like another carbon away from what it's stabilizing, right? What it's stabilizing is these electrons on that oxygen. And then if I was to compare that one to the third one, they're on the same carbon, right? They're both not adjacent, but one carbon away. But on the third one, I have a chlorine, and chlorine is not as electronegative as fluorine. So that one's not going to inductively withdraw it with the same strength that fluorine would. So just because it has an inductive effect doesn't make them all equal, right? So drawing their corresponding acids, this one compared to this one, compared to this one, these are more acidic. The last one we're going to look at are hybridization effects. So number 4. So the hybridization of the conjugate base also affects the acidity of HA. So the hybridization of the conjugate base also affects the acidity of our acid HA. So just want to make sure everyone remembers this. So if I was to compare just an s orbital, and I'm drawing my set of axes, which I'm really horrible at. I do this every time. I want those to all cross at the same point. I don't understand how math people do it perfectly every time. Practice, I guess. But if I was to draw an s orbital, my nucleus is going to be in the center of those axes. And then my orbital, right, is spherical. So those electrons are most likely to be found in the spherical region of space centered around that nucleus. I'm going to draw the same set of axes. Again, my nucleus is in the center, and then I'm going to put a p orbital on here. Let's make this smaller so we can do that. P orbitals have 2 lobes, and we could draw 3 of them all on our different set of axes. But right, they have a region that's above and then a region that's below. And I'm just going to draw one of them, but we could have drawn them on the x or the z axis. But if we look at the p orbital, there's no electron density where the nucleus is. The orange highlighter that I put on there does not touch the green dot in the middle. My s orbital, that electron density is all around that nucleus. That makes s orbitals more stable, right? Or the electrons in s orbitals more stable, right? The electrons are negatively charged, our nucleus is positively charged, and they're attracted to each other. So the closer those electrons are to the nucleus, the more stable they are. So electrons in an s orbital are lower in energy than electrons in a p orbital, right? That's why we always fill up our s's before our p's when we're doing orbital electron configurations, right? So electrons in an s orbital are closer to the nucleus, right? There isn't a node. The node is that space around my nucleus in my p orbitals where I don't have any. I just don't like my size. It looks like it's smaller than my s orbital. It shouldn't be. That node is that center where there aren't any electrons. Let's actually put the word node on there. Node. Okay, this is a region with no electron density. And that node is right where my nucleus is. So electrons in an s orbital are closer to the nucleus than in a p orbital. So lower in energy and more stable. Right? Remember, the closer electrons are to the nucleus, the more stable they are, right? They're attracted to the nucleus, they want to be near the nucleus, and if they're far away, that's not so cool, right? They like to be close. So the closer they are, the more stable it is. P orbitals, because of that node, the electrons are not centered around the nucleus like they are in an s orbital, making them less stable. So if we remember, when we were talking about hybridization at the beginning of the semester, sp3 orbitals, right? These are 1/4 s, right? We're taking an s and we're taking our 3 p's and we're combining them so they have 1/4 s character. If we were to draw it, right, they kind of look like a p orbital, but a little bit shorter, but not that much shorter because they're only 1/4 s. If I was to look at an sp2 orbital, these guys are 1/3 s character, right? They're a little bit squattier, the electrons are a little closer to the nucleus, but they still have 2 parts p for every 1 part s. If I look at an sp orbital, these guys are half sphere, right? These are half s character. So the electrons in it are more stable than the electrons in an sp2 because it has more s character, right? If we were to look at its 2 lobes, right, it's a little bit rounder. My nucleus is right where that node is. If I was to look at this one, a little bit bigger, a little bit longer, we should say. And if I was to look at this one, a lot more p looking. So because it has more s character, the sp, the electrons in it are more stable. Sorry, I just want a different color here, not the highlighter. So as I go this way, right, electrons technically closer to the nucleus, so more stable. Right? The more s character we have, the more stable the electrons in that orbital are going to be. So going back up to this, the higher, not that you can read what that says. That's not any better. That's better. The higher the s character of the orbital, the more stable Actually, we can just leave it at that, the more stable. So by higher S character, I mean more percent. So half is higher S character, right? It has more S character than a third or a quarter. So more stable. So if I was to compare, sorry about that, guys. This one, so CH3, CH3, just 2 carbons. Right? I'm not drawing, its geometry is kind of messed up. Usually I try to draw the geometry. Let's just do it so we're in the habit. Just because I draw it bad doesn't mean I want you guys to draw it bad. So my 2 carbons, hydrogen, so tetrahedrals, double bonded carbon. So I have a sigma bond and a pi bond, right? sp2 hybridized carbon, so there's a p orbital on each of those with my pi bond between them. And then we add our triple bond here where I have 2 p orbitals in each carbon, 2 pi bonds, and then my sp orbitals overlapping to form that sigma bond. So looking at their conjugate bases, I have a lone pair, and you can take any of the protons. I'm just choosing to take that one. Actually, let's be consistent. Sorry, guys. I know it's annoying when I rewrite it, but I'm afraid if I draw stuff from different perspectives, it's probably going to be even more annoying than if I have you redraw it every time. Eventually I'll start doing that because I'll expect that you know you can just rotate this molecule, but we haven't really talked about that yet, so I'll just redraw it and stick it there. So this is the conjugate base, right? And conjugate base for this one. Conjugate base. Right, so you react this with a base. We also have a conjugate acid as my other product. We just don't really care about it. At least right now, we don't really care about it. So if I look at these, right, this carbon is sp3 hybridized. This carbon is sp2 hybridized. This carbon is sp hybridized. And we know that electrons in an sp orbital, if we go back up to this, are more stable because it has more s characters, so they're closer to the nucleus. So because this conjugate base is more stable, this acid up here that I'm currently circling is more acidic. So more stable conjugate base. Because it has, we should say because the orbital that the lone pair are in has more S character. So its electrons are closer to the nucleus. Then with the sp2 and sp3 hybridized carbons. So don't forget my hydrogen there, is the stronger acid of the three. So electrons in an sp orbital are going to be more stable than electrons in an sp2 hybridized orbital, which are stronger than electrons in an sp3 hybridized orbital, making, if I go back up to my acids here, these my stronger acid, right? These guys are my stronger acids, these ones here. Because these are more stable. Conjugate base. I just want to make sure when you're explaining, you differentiate between your conjugate base and your acid. Let's do. So what we're going to do after I finish drawing these is we're going to determine what's favored. Sorry, this should be a hydroxide. What's favored at equilibrium, my reactants or my products. Alrighty. So kind of where I would start is you don't have to label them on paper. You don't have to write it down unless I'm asking for that, of course. But you do need to know which are the acids and which are the bases in your head, because you need to pick the stronger acid or the more stable conjugate base. You need to know what those are. Like if I say, which of the two acids is stronger, then you need to know what the acid and the conjugate acid are. So until you can just look at this and say, oh, well, that's obviously the conjugate base, I would label them. Just so when you're going through it and you're writing your explanations, you're not going to goof up. So this is my acid, this is its conjugate base, and then this is my base, this is my conjugate acid. So what I would do is I would look at the two bases, I would determine which base is more stable, and then that means its corresponding acid is stronger. So I'm going to compare this base, which is the conjugate in the reverse direction, to this base, and I'm going to say of those two bases, which is more stable and then why. If I determine that my hydroxide ion, the one I just put the star at, is the stronger base, then water, over here where I just put the arrow, is the stronger acid, right? I'm more likely to form the more stable thing. If I determine that this is my more stable conjugate base, right? Just put the star on. That means that this acid, where I just put the arrow, is the stronger one. Right? We're not given pKa values, so we can't go on that. We can just look and say, okay, of the products, which one's more stable, right? Which one do we want to form? The one that we want to form is the one we're going to form. So comparing this base to this base, which one do we like better? And then why, of course. Well, you guys are thinking about it. I'm going to fix that hydrogen because it's messy. So what do you guys think? Hopefully you're going to pick this one. If you don't, you're still learning, so don't beat yourself up for it. It's okay. This is the more stable base. And our reason for that is it has resonance. Right? If I was to look at this structure, there are 3 lone pairs on that oxygen. That's how we get that negative formal charge. And I can move those electrons in. There's actually quite a few resonance structures you can draw for this one. Those are still there, but then that pi bond, I move those electrons out onto that carbon. And then you can actually keep going. Those can actually go in, they can go out onto this carbon. This is good resonance practice for you guys. They're getting smaller as I go. Our atoms aren't shrinking, it's just me. So those are there. I moved the lone pair in to make that pi bond, and then I have a lone pair sitting out on that carbon with the negative charge. And then you can do one more, you can move those in, you can put the lone pair out there. Let me just stop there, but it does have resonance, it has lots of resonance. So because that base is resonance stabilized, it's more stable, so we would rather form that base than hydroxide ions. Hydroxide ion is not resonance stable. So not as stable as this one, which is a phenoxide ion. Not that you need to know that yet, but that's what it is called. It's just even too messy for me. So which one's going to be favored? The forward direction or the reverse direction? Do I want to make the more stable thing, or do I want to make the less stable thing? Yeah, I want to make the more stable thing. So products are favored. Right? Because this base here is more stable than this one here, we would rather make the more stable one. So I'm going to go in that direction. This acid that I'm currently circling is more acidic than water. Another example. So same sort of idea, we want to know which direction is favored at equilibrium, just given this, not given pKa values or Ka values. So this is my acid, my base, my conjugate base, and my conjugate acid. Again, remembering that if we're looking in the reverse direction, the conjugate acid is just the acid, the conjugate base is just the base, and then the reactants that I have labeled acids and bases are my conjugates. So when I say identify the two conjugate bases and I put a box around this one, if it's confusing, that is the conjugate base in the reverse direction. This one is the conjugate base in the forward direction. So identify the two bases. And then of those two bases, which one is more stable? Thoughts on that? I'm gonna pick this one. If you pick the oxygen, you're getting your trends mixed up. So if you look at your periodic table, sulfur and oxygen are in the same group. So if you're thinking oxygen's more electronegative, we want to have the trend on that, or we want to have the negative charge on that one. That's when we're going across. Remember, when we're going down, we're looking at size. So sulfur is more polarizable. It's bigger, it can handle that better. So more stable, sulfur is more polarizable. This is the one where if instead of looking at the two bases, if you want to look at the two acids, that's fine. Breaking that SH bond versus breaking that OH bond, right? So is it easier to break that bond or this bond, right? The sulfur hydrogen bond or the oxygen hydrogen bond? This one is easier to break. Because it's weaker. And then if you just leave it at that, I'm going to say, why is it weaker? Because the orbitals that overlap to form that bond are more mismatched. By that I just mean the size is more different than with oxygen and hydrogen. than in a oxygen-hydrogen bond. So whether you want to look at the conjugate bases, this one, or the actual bond that we're breaking, either way we're going to get the same answer. If it's easier to break the SH bond, we're going to break that one, and we're going to go in the forward direction. If you look at this being more stable, we want to make the more stable thing, so we're going to go in the forward direction. So this one, the forward direction is favored also.